Hello everybody. In this session, we are going to discuss MOSFET amplifier biasing and configurations. There are two different environments in which MOSFET amplifiers are used. The first one is the discrete circuits. In the discrete circuits, amplifier is made of transistor and some other external components like resistor and capacitor. But in the integrated circuits, everything will be fabricated on a single chip. So the method of biasing a transistor amplifier will be very different for these two environments. The primary reason is because usually it is very expensive to fabricate a resistor and large capacitors on integrated circuits, and this is not a problem for discrete component circuits, where external individual resistors or capacitors can be used in the circuits. For the discrete MOSFET amplifiers, there are a couple methods we can use to bias the transistor. They are almost identical to the BJT-based amplifier circuits. For example, here, the first one here, biasing the transistor with a single voltage supply. Here we use a voltage divider to provide the gate voltage, and also use RDRS to generate a reasonable drain and source voltage. In the second configuration, we are using two voltage supplies. This is a positive voltage supply, this is a negative voltage supply. In that case, we can connect the gate to ground through a larger resistor here. The last one actually we have discussed before. In this one, we connected the drain and the gate through a larger resistor. In this way, we can guarantee the transistor is working at saturation mode if our VDD is larger enough. Our VDD is larger than VT. Now here an example how to design a biasing circuits using a single supply VDD equals 15 volts and also a fixed voltage at the gate to establish a DC drain current with ID equals 0.5 milliamps. Given that our VT equals 1 volt and Kn prime W over L equals 1 milliamps per volt square, and lambda equals 0 means we ignore the early effect. We can use the similar rule we have used in BJT-based amplifier. So this is the 1/3 rule. So use the rule of thumb, we can provide 1/3 voltage drop across this RD, and 1/3 voltage drop across the transistor, and also 1/3 voltage drop across the source resistor here. And with this rule of thumb, we will be able to calculate our RD and RS. So 1/3 will give us 5 volts voltage drop on each component, and then we can calculate our resistance here, which is 10 kilo ohm. Since the transistor is working at saturation mode, we can use the saturation equation here. Now in this saturation equation, the only unknown is VOV, and we can calculate that will give us VOV equals 1 volts. And we know VOV equals VGS minus VT, so that means VGS equals VOV plus VT. VT is 1 volts already, so 1 plus 1 gives us 2 volts. So VGS gives us 2 volts. Our voltage Vs now can be calculated through the voltage drop across the resistor at the source. So that equals RD times RS, that will give us 5 volts. So Vs equals 5 and VGS equals 2, so which means our gate voltage should be 7 volts. In order to achieve the 7 volts gate voltage, actually is very simple, because our voltage supply is 15 volts. We don't have any current into the gate, and we can just pick up two big resistor or larger resistor here, 7 mega ohm and 8 mega ohm, will give us a gate voltage at 7. To bias the MOSFET amplifier in integrated circuits, the DC current source are usually used. So the current mirror circuits are often used to provide the current source. So the basic current mirror, which is shown here, is basically the same as we saw in the BJT-based current mirror. We have these two matched transistors here being connected gate to gate. Both gates were connected to one of the transistors drain. In this pair of transistors here, and Q1 actually is forced to operate in saturation mode because the drain and the gate are connected. And we have discussed this before many times. When the drain and the gate are connected, and the voltage here will be equal, as long as VDD is larger enough, this transistor will always work at the saturation mode. And in the saturation mode, we can use the saturation equation to calculate the drain current for this Q1 transistor. Because we don't have any gate current, the drain current of this Q1 transistor must equal the reference current. So the reference current can be calculated from the voltage supply and minus the voltage drop between gate and the source, that is VGS, and minus the negative voltage supply. Because the VGS for both Q1 and Q2 are the same, so the drain current in Q2 can be expressed by this formula here, which is also a saturation equation. Now, if Q1 and Q2 are perfectly matched, which means their Kn prime are equal and also their threshold voltage are equal. But they might be fabricated with a different dimension. And in that way, we can find out the relationship between their drain current, which is determined by the dimensions of the transistor here. Now, this gives us some advantage to design different current mirrors. Now, in this current mirror, this Q2 will act as a current sink because it pulls the current RO from the load. And that's because they are the NMOS transistor. If we are using PMOS transistor to make the current mirror, so the current mirror will be constructed in this way. And here, the Q2 act as a current source that will push the current and into the load. So this will push the current into the load. The MOSFET amplifier configuration will be almost identical to those of BJT-based amplifier. Basically, we have three configurations. Common source amplifier. This also include configurations with a source resistor. Sometimes we call it source degeneration. And common gate amplifiers, and common drain amplifiers, and the common drain amplifiers also called a source follower. As we mentioned, there are two different environments in which the MOSFET amplifiers are used. So discrete circuits and also integrated circuits. So the method of biasing transistor amplifier are different in these two environments, and we will separate our discussion in these two environments. In the discrete MOSFET amplifier, it is no problem to use a larger value resistor and a capacitor. So the basic configuration can be used like these three here: common source amplifier, common gate, and a common drain or source follower. In common source amplifier, we input our signal at the gate, but taking the signal out from the drain. In common gate amplifier, we input our signal to the source and taking out our signal from the drain, but we ground our gate. In the common drain amplifier, we input our signal at the gate, by taking out our signal from the source. That's why we call it a source follower. As we discussed earlier, larger valued resistors and capacitors are not often used in the integrated circuits environment because of the difficulty in fabrication. Instead, we can use active load to bias the transistor. As shown here in this configuration below, and we can use some current source to bias the transistor. Those active load are usually the non-ideal current source. For example, we can use current mirror to generate that current source. So here is the common source amplifier configuration, and instead of using RD, and we can use a current source to replace RD here. For common gate, we do the same thing to use a current source to bias the transistor, and in common drain, we will have the similar configuration. This is a short discussion on the biasing transistor and also the amplifier configurations. In future sessions, we are going to discuss all this common source, common gate, and common drain configuration in details, but separate them into a discrete environment and also integrated circuits environment. Before we go for that discussion, I want to have another discussion on the body effect. And, this body effect is unique to MOSFET. We don't see that in the BJTs, but this plays a significant role in MOSFET. See you next time.